Graeme, and I'm a PhD student at the Institute for Gravitational Research.
What do you like about your job?
What I like about my job is variety. So I'm not sat at a computer doing analysis 9 to 5. I break it up by going into the lab, by doing experiments in different labs. So one day I could just be doing analysis for a couple of hours, like working on results that I've got from another experiment, and then go into the lab, do something with my hands, and do a completely different experiment. So that's what I quite enjoy about it.
Can you maybe just explain a bit about what the room you're in just now is?
Yeah. So this is my own lab, which is very rare to get as a PhD student. Most postdocs, like people who have got their doctorate, don't even get a lab for themselves. So the lab I have here is used for cryogenic research, so making things very, very, very cold, down to 4 Kelvin minus 270 odd degrees Celsius. So I have my cryostat behind me, which you might just be able to see if I raise the camera up. So that gold plate at the bottom gets to 4 Kelvin, but I have to cover it all up with like a kind of inverted Russian doll design. So there's lots of chambers that go on it, and you pump out all the air. And the reason I do that is because the next generation of gravitational wave detectors are going to be cryogenic, whereas the ones that we currently have around the world run at room temperature. So this is basically the lab where I do a lot of my cryogenics research. But this is one of about 6 labs that I work in. So there's quite a lot of different labs with different instruments inside.
Cool, thanks for that. Milne, are you able to unmute yourself to ask the next question?
Yeah.
So I wanted to take a STEM-related career because I fundamentally enjoyed STEM subjects at school, and also just looking at the kind of job opportunities that you can get from a STEM-related career in research, in industry, just massively interested me. There's a lot of exciting technologies that we're always developing, and I kind of wanted to be on top of that and understand them. So that's why I went down that route.
What are your career aspirations?
So I'm a bit of an odd one out. I haven't followed a normal career trajectory. So I did my undergraduate at Glasgow University, same place here, in astrophysics, and then I worked in industry for 3 years as a stealth scientist for the Navy, and then I came back to do a PhD. So I don't want to go into academia, which is what the natural path is. If you've got a doctorate, many people will go and do a postdoc and work in a research institute. But I actually want to go into aviation, so I want to fly light aircraft, kind of completely unrelated to this, small aircraft in remote areas around the world. So places like Alaska, South Africa, doing kind of bush flying, aerial surveying, that kind of thing. And the ultimate aim one day is I'd like to combine it into what's called scientific aviation. So I'd like to fly aircraft for atmospheric research, for aurora borealis research, and things like ice sheet measurement thickness of the British Antarctic Survey. That's kind of the direction I want to head in.
Are there any negatives to your jobs, and what are the toughest parts?
The negatives, there are always negatives to every job. I'm lucky in that there's very few. Some days are tough. A PhD in particular is difficult. And say right now, actually, I've got about a year left, just over a year left in my PhD, and it's quite difficult because a lot of results I'm getting at the moment are, a lot of the experiments we're doing are not working. And that's very common in experimental physics. You will plug something in, or you'll set something up, you'll run your experiment, and something breaks, or something doesn't seem quite right, and you can't explain it, and it can be quite frustrating. It really can be frustrating, and I get frustrated quite easily. And I'd say that's one of the toughest parts, is just trying to push through when you have experimental failures, which keep happening. But, you know, trying to look on the bright side that you are making improvements as you go. So I'd say that's kind of the toughest part, particularly in experimental physics, is that things break quite a lot.
What do you wish you'd known when starting out in this career?
What do I wish I'd known about when I was starting out? That's a difficult one, because there's so much you don't know, but that's kind of naturally part of the PhD, is you learn it. I guess, again, going back to what's the toughest part, is just knowing how common it is and how often it is that things fail. When you read scientific papers, when you see research in the news, you only ever see the final result, which people may have taken a year to get, and may have taken 10 years to get, in some cases 50 years to get. So you always see people's research as like, oh, it's perfect, that's amazing, I wish I could do that, without realizing that they've actually taken hundreds, maybe thousands of attempts of it breaking, going wrong, not understanding things, to get to the stage where they could publish a paper or make a big discovery on it. So I think I wish I'd known how difficult the research is, you know, how many mistakes you have to make to get to the right answer or get to a publishable answer.
Graeme, do you have any advice about kind of dealing with that failure, or like pushing through with mistakes or anything like that? How do you keep your morale up?
In terms of pushing through mistakes or getting past mistakes that you make, is one thing I've learned, certainly with PhD, is not to compare yourself to other people. And I definitely I did that when I did my PhD. When I started my PhD, I was like, oh, these students are doing, look at all these wonderful graphs and results and data they have, and I don't have any of this. But I've learned that, again, a PhD by its very definition is very unique. No one does what you do. That's kind of a prerequisite of the PhD project. So learning not to compare yourself, and the same I'd say even in school, like not comparing yourself. If you've got a friend who's got all A's and you don't, that's not an issue. Try and just concentrate on yourself and not worry about what other people are doing.
When did you decide to become an experimental physicist?
So I think I decided that when I was in my old job in industry. I was working on board ships and submarines, and again, it was a varied role. So I do a lot of analysis and data analysis, but I'd also be physically on board ships and submarines in overalls, like an engineer, down in the engine room or whatever. So I'd be doing a lot of stuff with my hands. I'd be learning. I learned a lot of skills in that job in terms of like tool work, in terms of teamwork. And when I went back and did a lot of data analysis, I was thinking, well, this is a really nice combination of looking at data, applying it to the real world, in this case a submarine or a ship, and getting real world results, and also doing the work beforehand with your hands. So being there, building an electronic circuit, fixing a circuit, working with tools. And I think that was the point when I realized that I kind of missed a lot of research. I missed a lot of that kind of you know, big breakthrough science and big exciting stuff that kind of made me interested in studying physics in the first place. And then I thought, well, I can maybe combine the two by going back to university and doing a PhD in experimental physics. And in this case, it is a particularly hands-on PhD. A lot of what I do is, you know, 80% of what I do is in the lab, which is quite a high percentage. So I think that was the point about 2017 that I decided I definitely ought to go back and become an experimental physicist.
Interested in STEM subjects?
Yes, yeah, I'd say I have. It's not something I would say that developed. I don't know where it came from. I think from a young age I was interested in planes, which is why I still want to go into aviation. And there's obviously a lot of technical aspects to aircraft in terms of how they fly, in terms of engineering. And you hear it a lot. It's a very stereotypical thing, but I was keen on taking things apart, seeing how they worked, and trying to put them back together, not always successfully. But so I've always been interested in STEM subjects because I think the way you learn and the way you study it is quite exciting, and especially when you get to the higher levels where you get to actually do your own stuff and you get to see the results of it, that kind of just encouraged me more.
I noticed on your profile you said that young people shouldn't define themselves by the grades they got. Can you elaborate on that statement? Is that like a personal experience for you? Yeah,
so I am a big advocate of people not being defined by their grades, and that is from personal experience. I'm not a straight A student. I am straight A when it came to physics primarily, but then my undergraduate degree was a 2-1. I didn't get first class, and also I don't have a master's. A lot of people, I don't know where it comes from, but a lot of people think you need to have a master's to do a PhD, and that's not true. So you always see these people get straight A's at school in every subject and go off to university, but that just doesn't seem to be the case nowadays as well. Just because you don't get all A's does not mean you cannot go to university or college or do whatever it is that you want to do. And there are some like pragmatic reasons. You obviously need to study hard and get good grades, but also I think part of the reason I got to do a PhD without a first class degree and without being a straight A student is because I did so much other extracurricular stuff as well in my spare time, whether it be volunteering, whether it be kind of sports stuff, whether it be obviously working in industry. That was a massive factor which led me into doing the PhD. So I think, yeah, making sure you have like a wide range of things that you do rather than just straight academic stuff, even if you're going into an academic environment, is quite beneficial.
What do you expect from the next generation then?
So I think the world as a whole expects an awful lot from the next generation of STEM leaders. There is a massive weight on the shoulders of young people at the moment. 2020 is a prime example. And there's a lot of obviously like negative stuff happening at the moment between coronavirus, between climate crisis that we're in at the moment. You know, that's not going to go away. And although it has a lot of negative, it can seem an awful lot of negative and a lot of hard work, it is going to require an awful lot of young people working in a wide variety of disciplines, not just physics, not just maths, not just biology, not just chemistry, and including things like the social sciences and the arts. It really does require a lot of everybody working in all the subjects to work really hard to tackle these problems. So I think there's going to be an awful lot expected, but at the same time, that should provide an awful lot of opportunities for young people who are interested in STEM subjects, because we need more scientists and we need more engineers and mathematicians. So I think hopefully it will generate more work for young people interested in STEM at least.
Are there any areas you want to see explored further?
I suppose my own field I'd like to see explored further. I mean, that's happening anyway. So this is why we're working on the next generation of gravitational wave detectors that allows us to detect black holes, neutron stars colliding further away into the universe, hopefully up to the edge of the observable universe. And also smaller ones closer to us will be able to detect those signals as well. So there's a lot of areas in generally in science that need explored further. I think even in particular, the way we learn science needs examined more. The way you're taught to be a scientist, one thing I've noticed is like you're taught in a very particular way, but I think more interdisciplinary, multidisciplinary work between teaching the way social scientists learn, the way artists learn, the way scientists learn. I would like to see that explored further, and I think that'd be massively beneficial to the sciences because it changes the way you think. And that is massively beneficial. So in actual fact, I'd like to see more research and more interdisciplinary research, which is happening quite a lot at the moment, which is nice.
Graeme, I wonder if you could explain a bit about what your research is and maybe what gravitational waves are and why it's important that that you research them. Yeah,
so gravitational wave research is very much a fundamental physics and astrophysics and astronomy research. It's about the study of predominantly things like black holes or neutron stars, so very, very, very dense objects, lots of mass in a very, very small area of space. Typically spinning around each other, orbiting around each other, so two black holes, two neutron stars, or a black hole and a neutron star, spinning around, and as they spin around at, you know, fractions of the speed of light, then they send out these ripples in space-time. A bit like two corks floating on a pond. As the corks spin around on the pond surface, then you would see these ripples sent out. So those ripples are gravitational waves. My research as an experimental physicist is to work on the detector side, so less the astronomy side and the data side, more how can we make these detectors as sensitive as possible. These are the most sensitive detectors on planet Earth. They're detecting tiny changes about 1,000th the diameter of a proton. So that requires vast amount of research and technology to make these mirrors the most still things on planet Earth, the mirrors that reflect the lasers that we look at the signal to see if we've detected gravitational waves. So a lot of that research goes into making them as sensitive as possible. And my research is taking the current generation of gravitational wave detectors and cooling them down, because if you cool them down, you make the atoms more still. If you make the atoms more still, then you can make your detector more sensitive. But in doing so, we need to use a new material. So currently we use glass, which is very, very, very pure form of glass called fused silica. And instead we're moving to silicon, the stuff that's inside your phone and electronic circuits, because it has very good properties at cryogenic temperatures. So I am trying to build a suspension, so a sort of ribbon of silicon that can hold a mass on the bottom of it, and cool it down to cryogenic temperatures. And I'm finding it's very challenging. Naturally, it's very difficult to work with, but you know, we're making good progress on that. But although gravitational waves are very much a fundamental physics problem, there are a lot of spin-off technologies, as is always the case with blue skies research or very fundamental physics research. There's a lot of practical applications. So the coatings that we use in our mirrors to reflect the laser light, a team over at Strathclyde led by a friend, Professor Stuart Reid, they discovered that the technique used to coat the mirrors, called nano-kicking, you can apply this to stem cells, and they're applying it, I think, to bone growth at the moment, because one of the issues with stem cells is you can never make enough, because as soon as you start making cells and growing them, then the first cells start to die by the time the later cells start to grow. Whereas by nano-kicking them, by applying the same technique to these cells, you can actually grow fairly large samples, I believe, of stem cell material, which hopefully I'm told may one day lead to us being able to regrow bone rather than having grafts and things like that, which would be pretty useful. And on top of that, we also have a subgroup in the Institute for Gravitational Research called MEMS. They work on little electronic devices, and they work in gravimetry. So they are working on tiny little gravity sensors. Hopefully one day you might be able to fit in the size of your phone, maybe a bit bigger. But you can place them all over a volcano, and you can tell much sooner than normal seismology and earthquakes. You can tell much sooner that magma is building up, because if magma builds up, the density underneath increases, the force of gravity increases. So you can create early warning systems for volcanoes before they're about to erupt, to get people out and evacuate them out from the zone before they're in danger. So there's always a lot of spin-off technologies that, and people are right to ask, you know, what's the point of us studying X, Y, and Z in physics? But the technologies we use to get there normally have a lot of fairly immediate advantages to society that we can use to our benefit. So,
are there any areas of STEM you feel don't get enough attention, like anything has loads of untapped potential?
Areas of STEM that I feel don't get enough attention. It's difficult. The way STEM research works is, you know, it's funded by funding councils, so they kind of sort of determine where a lot of the funding goes and what's popular. A great example is coronavirus. I've heard from friends who are virologists. They were working on other viruses. Now everybody's working on coronavirus because that's where the funding is at. So I can't say anything for any other subjects, but physics and astronomy, I think most areas seem to be getting attention, and all the areas that are being researched are extremely exciting. I think really that's not for me to decide, it's for the future generations to decide, to look at the research and decide where the gaps are, where are we missing, or what can we build on knowledge-wise that we don't already know. So I think really it's up to the next generation of STEM leaders to look for that untapped potential and to go out, do the discovery, do the research, and make these exciting scientific breakthroughs.